welcome to the video on reciprocal circular functions. In this video I'm going to have a look at what these functions are, and then we'll have a look at the graphs of them as well and see how we can create those based on our knowledge of other trigonometric graphs. So to begin with, the three reciprocal circular functions are cosec, sec and cot. So cosec is defined as 1 over sine theta, sec is defined as 1 over cos theta, and cot is defined as 1 over tan theta. Now, there's a nice way to remember this, and that is just pay attention to what the third letter in each case is, because that tells you basically what it's over. So, for example, the second one, sec theta, the third letter is a c, so it tells us it's 1 over cos theta. Now, for each of these, I've got the graphs of the original functions drawn. So, what I've got here on the first graph is just y equals sine theta, or y equals sine x. And so I want to use this to create the reciprocal graph. Okay, and so I'm going to do 1 divided by this. Now, the number that I'm going to be dividing by here in each case is the value of the function, which is the y coordinate of it. Okay, so to begin with, there are a few places where this graph has a y coordinate of 0, and so 1 divided by 0 is going to be undefined. And so at those places we should put an asymptote. So wherever the height is 0, which we can see that's along the y-axis, I'll just put a bit of a scribble here to kind of show that it's an asymptote. And over here on the left-hand side, we're going to have an asymptote because that has a height of 0. And we've also got one here. And here. And also over here. So that's the first thing. Now I should label the equations of those asymptotes. I will do that towards the end. The next thing is we have a few places where the function is equal to 1 or negative 1. And so when we have 1 divided by 1, that's going to equal 1. And when we have 1 divided by negative 1, that's just going to equal negative 1. So that's going to give us points here and here, and also down here and down here. There's another one over there, it's right on the end. Now for the part that's a little bit sort of tricky, and that is we're going to consider what happens as we approach a value like down here somewhere where we have a value that's really close to 0. And so what we're going to do there is think about what's going to happen if we have 1 divided by, say, 1/100th, okay? So 1 divided by 1/100th would be 100, which means that it's going to be quite a large y value which is produced. It's going to be up there somewhere. And same over this other side over here, so it'll produce a value up there somewhere. And so the shape of the graph is going to go something like this. Again, always approaching the asymptotes and never reaching them. Based on this, I'm going to have a similar feature out in this section. And, well, you could probably assume what's going to happen in the negative region of it. If we have 1 divided by a really small negative number, it's going to produce a really large negative number. So we get something that looks like that, and these other sections will get filled in the same way. So what I've drawn there in black is the graph of cosec theta, or y equals cosec theta. So a couple of features of this. Firstly, let's consider what the domain is. So normally the graph of sine x or sine theta would have a period of 2 pi. So this is 2 pi here, and that makes this here pi and 0, and, well, over here 3 pi and negative pi. So what we can see is that the graph exists everywhere except for well, multiples of pi. So we could say that the domain, remembering the domain is the x values, is going to be all real numbers excluding multiples of pi, which we can write as all real numbers excluding n pi, such that n is an element of the integers z. So that's how we can write the domain for the cosec function. As for the range, well, we can see that it includes all the numbers except for values between -1 and +1. And so what we can say is that the range of this is all real numbers excluding the interval of -1 to 1. Whoops. And in this case, the -1 to 1 is not included, so I'm using round brackets because I'm excluding the -1 not being included. So yeah, it's a bit of a thing to get your head around. Basically, the value of 1 and -1 is included. So yeah. Now, as you can see also with the graph, it does have turning points. They are in the same positions as the turning points of the normal sine curve. And the asymptotes. Now the asymptotes have equations, and I should label these on the graph as I said I was going to early on. So the one here would be x equals pi. The next one would be x equals 2 pi, x equals 3 pi, and so on. And also back over here, x equals 0 and x equals -pi. So really important that we label those features. But yeah, that's all the features of the graph. So if I scroll down to the graph of sec theta, well, it's basically the same graph, just translated across a little bit. So I'm going to draw this one really quickly because it's drawn exactly the same way. So I'll start with the asymptotes. Now again, the cosine function typically has a period of 2 pi. So I know that this is going to be 2 pi here. Sorry, that's not 2 pi there, that was my bad. In the wrong place. 2 pi would be this point right here. So based on that, well, that one there is going to be pi, and so that means that this asymptote here must be at x equals pi on 2, and this next one is going to be x equals 3 pi on 2, and then x equals 5 pi on 2, just following a pattern now, x equals 7 pi on 2. So basically the asymptotes are occurring at odd multiples of pi on 2. And then, well, it's going to have that same shape, so again, always approaching the asymptotes, but never reaching them. There we have it. So that's the graph of sec theta, or y equals sec theta. And so again, the domain here is going to be all real numbers excluding the asymptotes, which occur at odd multiples of pi on 2. So to make sure that it's an odd multiple, I'm going to go 2n plus 1 pi over 2. Such that n is an element of the integers. So the 2n plus 1 makes it so that it is always odd, because whatever value of n we put in there, we double it, which makes it even, and then add 1 onto it, which makes it odd. And so then the range of this one as well, we need to cover that. So the range of this function, again, should be all real numbers, excluding that same interval of, whoops, round bracket, -1 to 1. And yeah, I think that's about all we need to do for that one. So the last one, cot theta. This is a bit of an interesting one because we kind of need to use limits to figure out the shape of it, or at least a bit of, well, we could use a bit of common sense. So again, with this one, I'm going to start off with the places where the function has a value of 0, which is at the origin. So I'll put some scribbles on the y-axis just to show that it is an asymptote. And then I've got another asymptote here, again because the value is 0, and over here. And well, we don't really know what happens with the asymptotes just yet. Let's consider what's going to happen here though. So if I pick a point like down here somewhere, okay, well that's a very small y value. So if I do 1 divided by that value, I'm going to get a very large number. Over here, I've got a very large number as we're going up along close to the asymptote. And so 1 divided by a very large number is actually going to be a very small number. And then if I consider down here somewhere, we've got 1 divided by a very large negative number, which will be a very small negative number. And over here, considering this section, well, 1 divided by a small negative number is going to be a large negative number. So the graph ends up looking basically like a reflection of the tan graph. And do the same in this section. Yep, that's looking good. All right, so that's the graph of cot theta. And so then I just need to go through and have a look at labeling the asymptotes there. Typically the graph of tan theta has a period of pi. So this here would normally be pi, so that's where an asymptote is. So I'm going to just say x equals pi, and then for the next one, x equals 2 pi. And we can see that that's just multiples of pi as well. So then when we go to write the domain of this, that is all real numbers excluding n pi, such that, n is an element of the integers. And also the range of this one, well, it actually goes for all real numbers. So there's nothing that's excluded in this one. So one other thing that I will do here is I will mark in the coordinates of the x-intercepts because they might come in handy later on. So if this was an asymptote at pi, then that makes this here pi on 2, 0. It makes this one here 3 pi on 2, 0. And then 5 pi on 2, 0. And also back over this other side, negative pi on 2, 0. Alright. So if we just scroll down a bit further, sketch the following over the interval 0 to 2 pi, stating the domain and range for each. So y equals sec 2x. Well, that 2 is going to be a dilation by a factor of half from the y-axis, so the graph should be half as wide as it was originally. Okay, if I scroll back up just to have a look at the graph of sec, so it's this one just here, we can see that it sort of takes, well, it still takes 2 pi to go through a full cycle, so it should only take pi to go through a full cycle this time. So when I draw this one, I'm drawing it just from 0 to 2 pi, so I don't need to worry about it out the left-hand side of the graph. So x, y, the values of 1 and negative 1 are still going to be significant here, and it's just going to go up like this, have an asymptote, section, and then another asymptote. Okay, so what I've drawn there, that's one full cycle of the graph. So normally that would take over 2 pi, as we saw just up here. Okay, but because of the dilation by a factor of half, then this is really just pi here. And so then we'll just need to continue on. I might need to give myself a little bit more room to draw it out. So again, when you're doing these, try to have nice, even spacing. Okay, so there we see 2 full cycles. So that there's going to be 2 pi. And I need to go through and label the equations of the asymptotes, that sort of thing. So what have we got? We've got pi. So there's pi on 2, which means that this first asymptote is at x equals pi on 4. Second is at x equals 3 pi on 4. Third is at x equals 5 pi on 4. And then x equals 7 pi on 4. And yeah, there we have it. Again, this can be done using your calculator. You just write in y equals 1 over cos 2x and then go from there. As for the second one, y equals cot of x minus pi on 4. So the x minus pi on 4 moves the graph pi on 4 units to the right. I guess I should actually finish up the last question properly because I haven't done everything yet as well. So the domain of this one, what's a good way to write this? Perhaps I could say 0 to 2 pi, excluding just a moment. Now it's odd multiples of pi on 4, so I'm going to make that 2n plus 1 pi on 4. No, I can't really say that, can I? Because that would only mean a couple of those of n. So I'm just going to say excluding pi on 4, 3 pi on 4, 5 pi on 4, and 7 pi on 4. And anyway, the range of this one as well is going to be all real numbers excluding -1 to 1. Right, onto the graph of cot now. So again, sketching from 0 to 2 pi. I should label this x as well. So we look at the graph of cot. Normally it has an intercept of pi on 2. So that's moved across pi on 4 units to the right, which, if I just break this up into intervals of pi on 4, pi on 4, pi on 2, 3 pi on 4, and then pi, 5 pi on 4, 6 pi on 4, 7 pi on 4, and 8 pi on 4, which is 2 pi. So we had pi on 2, which has now become 3 pi on 4, and 3 pi on 2, which is now 7 pi on 4. So those are our 2 intercepts. And the asymptotes are also translated pi on 4 to the right. So those asymptotes were at pi and 2 pi and 0. So that's going to be at pi on 4. And then 5 pi on 4. That's all we'll have in that interval. And so then I can just kind of draw the shape of it. Now I should also figure out the endpoints of this. So I might just give me a second. Okay, so just going to calculate the start and end points basically. So we'll do the y-intercept, which is when x equals 0. So that means y equals cot of negative pi on 4. So that is 1 over 10 of negative pi on 4. And, well, 10 of negative pi on 4 should be negative 1. So it's really 1 over negative 1, which is just negative 1. So there it is there, and we're going to have that sort of section there. Now, because of the cyclical nature of this graph, I know that it also has to end at that same height because it's repeating every pi, and so, you know, when we've gone across 2 pi, we've also got that same endpoint, which is at 2 pi and negative 1. Anyway, I'll leave that there. It's quite a long video, but yeah, we'll pick it up a bit more in the next one. See you later.